Hi everyone, we are back and we are about to get into our Pset 1 solution videos. So, in this article, we have to fill out and correlate what are the corners of our material's tetrahedron. So we have structure, and there's a process, and there's properties, and there's performance. So, performance. In this article, we were talking about nanocrystalline materials. So, we have a process where we take large grains, so millimeter, and we break them down into a nanometer length scale. So this process creates a nanocrystalline structure. So nanometer, nanocrystalline materials. And when you have a nanocrystalline structure, you have this thing called the Hall-Petch relationship, which will affect the mechanical properties of your material. Specifically, your yield strength will increase and the strain at failure decreases. So this will change the performance of those materials. Specifically, the materials will become much better in terms of being able to withstand force and not yield, but they will be very brittle. So that's number one. Let's get into these. All right, it's true or false, correct if it's false. For Bragg diffraction, we only need a series of regular space obstacles. Nope. What else do we need? We need a lambda that's on the order of the distance between our obstacles. We need also perfect constructive interference. So those are kind of our three conditions. Metallic bonds can break and reform at room temperature. Nope. They have energies that are above kT. Only intermolecular bonds can break and reform at room temperature. I must utilize a wavelength on the order of angstrom to investigate molecular spacing on the order of micrometers. No. I need to have something on the order of micrometers because, again, has to be commensurate with the distance between our particles. Ionic bonds can break and nope, we just said this. Only intermolecular interactions can break at room temperatures. Intermolecular interactions have an energy less than kT. Destructive interference leaves no signal. True, but it needs to be perfect. So perfect destructive interference. So that's a little caveat there. Covalent bonds are intermolecular interactions with energy of 100 kT intramolecular. Intramolecular interactions can break and reform at room temperature. No, inter. Ionic bonds share electrons. No, they take or give away. Metallic bonding has delocalized. Yep. Oxygen is an anion with a -6 charge. Well, it's an anion, but it's going to be basically -2 here. Van der Waals interactions are intramolecular, greater than kT. No, they're inter, less than kT. Less. All right. What type of bonding will be exhibited by CR? Well, that'll be metallic. Which, if any of these, can spontaneously break and reform at room temperatures? No, because, again, it's intramolecular. How are the electrons distributed? If it's metallic, they are delocalized. CaCl2. Well, and let's do MgO at the same time. Well, we need to go to our handy-dandy to determine the... so Ca, Cl, Mg, and O. So let's go ahead. Cl, I believe, is 3.16. But... So, yeah, Cl is... I don't know if I could erase that. So Cl has... And actually, I'm going to bring up Mathematica here. Cl, CaCl2, and MgO. Okay, we can knock these out. So to determine whether these are definitely intramolecular reactions, but if they're covalent or ionic, because they're not metals, if they're covalent or ionic, we need to look at electronegativity differences. So we know that Cl equals 3.16. We need to find where is O is 3.44. O equals 3.44. Mathematica is still thinking. And we need Ca and Cl, CaCl2, and then MgO. So we're over here. Do we have one more? No, we need to go up the top. Oh, here we go. Mg is 1.31. Equals 1.31. And Ca, oof. That's not good. It's 1. So we had, I think it was CaCl2. Let's go back to the problem set now. Let's go down here. So let's go over here. Let's go over here. So we have Ca minus Cl, or vice versa, and then Mg minus O. If the difference is greater than 1.7, and again, you can just do absolute value. PS, absolute value, absolute value, absolute value. So these are both going to be ionic, and so electrons are they're not going to break and reform spontaneously, but they're going to be localized, and one's going to be taken, one's going to be removed. Peak is a polymer, and peak structure has these big, basically aromatic carbon rings, and I think there's a couple of these O's here too. So polymers will have, in here, carbon-carbon bonds. Those are covalent, and they're going to be shared. But they're also going to have intermolecular. Specifically, for these polymers that have these big rings, they're going to have steric interactions. And because of that O, they're going to have polar interactions as well. So those are effectively the type of bonds that you'll expect to see here. And there we go. MgO. Mg is our cation, 2+. O is our anion, -2+. So gives away 2 electrons, gains 2 electrons. What about UO2? U is going to be 4+ because oxygen is 2-, and there's 2 of those oxygens. Iron, there's got to be 3+ because there's 3 oxygens, 2-. That's going to be 6, so we need electroneutrality. All right, last problem. Let's get to it. So I always think it's fun to, let's actually just draw the Lennard-Jones potential here, and then we'll set it up in Mathematica. So we're going to say ULJ equals 4 times epsilon times sig divided by r to the 12th, minus sig divided by r to the 6th. We are fitting here that epsilon is going to be equal to 0.9 joules, which is good, very kind of us. Our sig is going to be equal to 2.1 angstroms, which you need to multiply times 10 to the -10. And here we go. Now we can move down to here. We can get this out. We also know that force equals minus derivative of ULJ with respect to R. And we can now go through the rest of these problems. All right, so we are looking at first, so let's see, we discussed the potentials, blah, 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 blah. Colloid assimilation for chromium. What is the equilibrium distance between chromium atoms? So our equilibrium distance is going to be basically always this 2r distance between one another. So for chromium, if we look up the metallic radius, which is right there, this is second from the bottom. If we look at chromium, where art thou, chromium? Whether it is 1.3. So 1.3 is going to be our metallic radii. So metal rad chromium equals 1.3 angstroms. So our equilibrium distance is going to be 1.3 times 2, so 2.6. So we are going to solve, or actually we're going to figure out what is our equilibrium distance. So predicted by the potential. So predicted by the potential, we're going to have, we're going to take the derivative. To figure out our equilibrium distance, we have to set our potential, we have to find our minimum of our potential here. So we need to set the derivative of our potential equal to 0 and solve. So derivative of ULJ with respect to r, set it equal to 0, solve for r, and we can kind of see that that value is going to be this. So this is 2.35 angstroms. So that's going to be that distance between essentially our particles, our interatomic distance. So it's a little bit off. We were predicting 2.6. This is 2.3. So it's a little bit off there, but not too bad, but something to consider. It's far enough apart where we're a little bit concerned. So what is the equilibrium distance predicted by the potential? What is the distance at which the force is maximized? So now we can solve where derivative of force with respect to r is equal to 0. And you get 2.6 angstroms. What is the force at a distance, so force, where slash dot r goes to, where r is 3 angstroms. So 3 times 10 to the minus 10. So this would be our force at 3 angstroms. Draw locations on the draw these locations on the sketch of the LJ potential. Explain your results. Also, the stiffness mirror is predicted for the curvature of the potential. Mathematically, how do you determine curvature of a function? Curvature is just going to be the second derivative of u LJ with respect to r squared. Greater than 0, positive curvature. Less than 0, negative curvature. This is our equilibrium distance. This is where force is maximized. So this was like 2.3. This is what's 2.6. And then this was our force at 3 angstroms. There you go. That is it. So we will see you all in the next video. Bye.